1,000 cores and was in less than 5 seconds for one time step, but there's still 2,000 of them. And to give you an order of magnitude or idea, these problems, we cannot do them 2 or 3 years ago because they were just too huge. Afterwards, once we have talked about the future of the Code-aster with the functionalities and the HPC, how can we provide a great user experience for everyday researchers and engineers? Because of course we developed the software at EDF R&D with some significant capabilities, but at the end it needs to be used within EDF for the studies. So we've developed recently a guided user interface in order to produce a Code-aster command file. It's way easier to produce now a command file, and you have also access of all the settlement products behind it. So you have a direct link between now your command file and the mesh which you can be using. I don't know if the small video works, yeah. So that gives you an idea of what you can do right now with the Aster study. So that was out for the first time last year, and with significant improvements this year. There will also be some new functionalities next year. So here you see you have a huge building in which you can select now your groups, and you can zoom in, zoom out, visualize where you're actually putting your loads. And next year you will see the loads normally on the mesh, in a sense that instead of just clicking and seeing actually the group of nodes, the nodes will flash, or you will have an arrow showing where the pressure is, or maybe a linear condition on some specific degrees of freedom. And then one last point, so why do we do this in an open source software? The intents and the motivations for the open source software, the first one was to improve the reputation through increased use. So we need to show that our source code, our code, is good for nuclear applications. So if it can be used by anyone, it's a proof that we can be, I would say, counterattacked. Anyone can use it, and also they can test it and verify if it's good or not. We are just being very transparent, and everyone can have access to the source code if they want to. It's also a way to bring improvements and additional validation. If people in the open source community show us a bug in it, we will, and we see that it really is a bug, we will integrate it into our software development process and ensure that it won't be there in the next version. It's also a way to spread skills. So basically, the more people use it, the more service providers there will be for EDF. So we can actually have subcontracts with these companies in which they have the skills. And now also through teaching, if universities use it, well, we know that people will use it afterwards. And one of the main features is a natural vector for research. So as I mentioned it a bit earlier, when we have PhDs or postdocs, we ask them to develop in Code-aster, and it's a way to capitalize everything they've done. Otherwise, often we lose what has been done. In this case, we know that there will still be the code at the end. And of course, it's a way to have some partnership and encourage some code development. So if we work with the academics, it's a common software in which we can both work together. Was it complicated to do that? Well, there are 3 stages, I would say, since the opening of the code. The first part was the emergence, so when actually the code was made available, people started to download it, but it wasn't very, very big because it was still new and people are used to another code. It's hard to change things. And then after 5 years, it started to get better. We had the first code development partnership, so now we actually started to work with other users outside of EDF, and the forum began to be sort of self-sustained. At the beginning, when we had a forum, people had questions. We inside EDF had to answer back every message in order to encourage people to use the code. From 2006, it was not completely, but it was quite self-sustained. So the community is trying to teach within the community how to use Code-aster. And since 2011, it's speeding up. So there's a ProNet association that was created. There will be, I will have to give a small talk about it a bit later. But now we're around 80 members in 20 countries. So what about the future of this open source software? Well, we would like to have a well-established, self-sustained community around Code-aster, because EDF actually develops the code, invests money in it, and it's important for us that the open source community contributes also to the code, at least within the open source community. So that's the end of my first presentation about the open source code and the SadoMeca. Are there any questions about the code? No? All right, so I will just switch to my second presentation, which is an example of a study that was performed inside EDF to show you a little bit what kind of problems we're facing and how Code-aster can answer it. So this presentation, which is a bit more, yes, is everything okay? Yes? Oh yeah. Oh yeah, sure, go for it. Yeah.
I have a question about compiling, because the version we download by the site is sequential version.
Yes.
Right. And are there some instruction to compile multi-parallel version?
It's always easier to compile it in sequential, of course. So inside ADF, it's people in my I can't promise anything, but since we're facing this situation, I would say every 2 months, someone calling us and saying, I'm not able to compile it. We would like to develop a Docker in which everything will be inside except the MPI. We don't know if it's going to work out. We're working on it right now with our IT. Actually, they're doing it for us. And I cannot promise anything. It's we working on a proof of concept right now because other EDF codes are facing the same situations. And basically, if it works out, which I can promise, I would like to focus on that, is that everything will be inside the Docker, and you will have to plug in your MPI process. So if it works, it will be available, but I can't promise anything.
It will be a possibility to get Code-aster into a Linux distribution. I mean, the Debian package ready with MPI. Is it possible?
I'm not sure. It was not part of it. There's CAE Linux that distributes a specific version that has Salome Mecha inside of it, but of course it's not in parallel. Okay. And often you need to compile it. If you go with the binary version directly, since the architectures are not the same, I think you lose most of the efficiency of the MPI processes. Yes. So, but yeah, compiling a code in parallel is complicated.
I know it.
Personally, I can do it. So
yes.
I have people in my team that does it, but it's complicated.
Thank you.
Thank you. Question?
Any other question from the audience?
Yes?
I didn't understand very good about the parallel version. What is the problem with the memory that you are looking to solve with the new
Okay, I understand. So right now, if you use 10 cores, every core must have access to all the information of the whole problem. So let's say your problem should take 1 gigabyte of memory. Because you're using 10 cores, and they can be on different machines, you will use 10 times 1 gigabyte. The idea here is to split the problem. As a user, you won't see anything. Is to split it so that every part of the mesh will be split in different parts, and every core will have its own part of the mesh. As a user, you don't see anything. You will just have a command saying split it, more or less. And then so for the whole problem, you will still have only 1 gigabyte of memory. And that's one of the main problems right now, because we actually, Code-aster and the solvers are available and capable of solving big problems. But if you need a lot of memory, let's say on a machine that has 64 cores, perhaps you don't have enough memory on a single machine in order to do it. So in this way, you have a leverage not only of, I would say, computation force, but also of access to memory. Yes?
You're trying to compile or the cloud computing platform like, for example, Microsoft or Amazon.
Yeah.
Do you think it's possible?
We actually working on it right now. We do not only develop Code-aster, there are also other codes, so we regroup all together in order to, I would say, cope with this question. So right now there's another project inside EDF trying to put the codes available on a cloud platform. So right now there will be more or less a cloud for EDF users. It will be inside with sensitive information. And there will be another one that could be available for outside users. The model is still in thick. We're mostly trying to see if it works right now. Some users are testing it right now on some specific studies. So the inside version of the cloud will be within our own machines, and the outside would be on Amazon. So right now it's being tested with Amazon or OVH, one of the two. Well, and so far it's working in a sense that there is enough debit in order to do a simulation in 3D and use Mecha and visualize everything. So that's also, I would say, a second solution to compiling in parallel. So if instead of giving you directly the code that which you can compile, we can actually give you access to some clusters through this. Of course, this has a fee right now, so we're not sure of how we're going to do it. We're testing it right now, but that could be a possibility. If you want to use it on and not have any questions about how I'm going to compile it or make it available in a Linux distribution, we can actually just have a VNC viewer, so you could actually use it on Windows, connect to the remote machine, and just have a screen. It gives you, let's say, 15 images per second in order to do your simulation. It's still not available, but we're working on it.
Another question is a user interface question and
Yeah.
user interface improvement.
Yes.
In working with beams, one of the main problem of when you create a model is to check that your beam section is oriented correctly in space. Let's say a double T or IPE beam.
Yeah.
Is there a planning in the development to have a sketched section in the three-dimensional view of a structure in which you can analyze and check the orientation of all the beams?
It's on our roadmap on Aster study. I don't know if we'll be able to do it in 2019 or 2020, but the idea is that when you have a beam, you will actually, and once you have the beam and you have put the properties, you will have a 3D element behind it that will show it. Okay. So that's part. Same thing for the shells, for all the structural elements. So we've noted that it's very important because you see the beam in the mesh, but afterwards there are so many numbers in the command files that you don't know what is doing what. So it's part of it's part of our roadmap, but I can't promise it's going to be done within the next few months. Okay. We'll see. I will have my budget soon, and from there I will try to go with the priorities.
Basically a local XY axis, just because if your beam is not linear but it's complex and curved in space, having just three vectors along the beam to check, this is your principal axis with the just
maybe that
not,
could
not
be an
the
in-between
full design, but just a hint that
give you an
the
idea.
orientation is right.
Yeah.
Another question on the post-processing.
Yes, another question about post-processing of results. Now with ParaView we have to extract every result. Okay. With Stanley, just with standard result, we can elaborate it directly in Stanley. Is there in development process? Is there something like Stanley in graphical?
We're trying right now to work on an additional part of the guided user interface, in which you will click and it will generate not directly a Stanley-like, but it will still be ParaView, but it will be pre-done for you. in a sense that it will apply the filters, the common one. Let's say if you want to see the deformed shape with a factor 10, there will be a button that will do it. It will generate everything for you in ParaView, but it will still be in ParaView because it's it's a choice that was made that every EDF code will be using ParaView. There's a lot of money in it actually. So, and we share it with all the different codes. Because before, every code had its own visualization software, which actually costed a lot. So now we're trying to regroup everything. So it will still be in ParaView, but we're trying to add some new features that will generate some pre-made filters in ParaView for you.
Okay, thank you.
Another question. Speaking about, speaking again the post-processing tool. And now in Code-aster-day, I think also now, I don't know if there is some development, but if you go to make a simulation with shell element, there is not possibility to plot top and bottom in the same output. Really, this is not a big problem, but sometimes become a problem when you work for a small company or there is a non-expert user that
Understand.
post-process the result. So is it possible in the future to have a possibility to plot in the same image top and bottom of the shell element?
So to have a 3D view of the shell elements, more or less.
Yes.
Extrapolate, computed post-process.
Or it's not important that it will be 3D view, but every top and bottom.
Okay, I see.
The same
I think it's important right now. It's not in the priorities, but I mean, it's already documented that there's a need. A little bit like I mentioned earlier about the axis in a beam. It's also part of it, but I cannot promise that will be done within next year. But it's a recurring demand, if I can dare to say so. We are aware that it's hard to visualize.
Just another small question about
Yes.
the languages that are present in the documentation, and what will be the future for these documents, because we know that they are translated in English, machine translation from French, but what is the future?
Yeah, so the documentation is produced in French. I had the idea at first, maybe the dreamy side of me, that everything could be in English, and so we move on. In France, it's not possible, in a sense that for me, it would be normal that the code is available in English, but I'm paid to develop the code for the engineering units of EDF, and they all work in French, and they will produce documents in French. So from that point of view, I have no choice but to produce the documentation in French. Then I could also produce it in English. Then if you want to do such a thing, you need people that can write in English, which sometimes can be complicated in France, but also it takes a lot of time if I have to produce simultaneously the two documentation. And documentation actually is very expensive. We have around 23,000 pages of documentation, and maintaining it in double would be complicated. So of course we decided to go through machine translation. Before it was done using the Google's tools, before there was artificial intelligence. We tested a new software 2 years ago that uses actually input information of documentation that was translated by some actual real people. So you feed the machine in order to get some better translation. The results are much better than what you can see today. The problem right now is that we cannot today, it's complicated to just use the API of that software. So we're dealing with the producer of that software because we actually have a license for it in order to produce documentation in English. I don't think there will be directly a documentation in Italian, sadly, not within the next 6 months for sure. But yeah, we expect, I would say next year, we'll see if we continue with this automatic translation software or if we switch to another one. We are investigating another one. I had a meeting with some German people with that actually do some translation with deep learning. The results were quite interesting. But I would say it's not very expensive actually to translate, but since our documentation is produced every week, I cannot afford to translate it every week if I pay per character or per page. So perhaps what will be, I'm not sure, I can't promise anything yet, but maybe every 6 months there will be an update of the documentation in English. And the worst case scenario will be the English documentation will be 6 months late from the French. But that could be, I would say, documentation evolves, but not that much at the end, so yeah.
Okay, thank you.
Thank you.
Domande, question?
Any other question? Okay. I think you are ready with the other.
Yeah, I will just look at how much time I have left. We'll just do a small, there's time, right. So the idea here was to present an analysis in mechanics that was actually done by EDF using advanced, I would say, functionalities of Code-aster, and that actually was an industrial one, not only academics. So it was performed by many people, and it's about cylinder heads of emergency diesel generators. So if you look at this component, it's not the car itself, it's that big component over here. This is an engine that needs to be used only if there is a problem on the power plant. If there's, let's say, a big problem and there's no more electricity, you stop producing, you still need to have the pumps working in order to cool the core. And in order to do that, you need engines that will actually be producing electricity for that. So that's the component. And actually, we never use it because we never had any issues in France. But we need to ensure that it works. So we have a shut-in, shut-out every 3 times a year, more or less. And this is what gives electricity to the power plant if the power plant cannot produce electricity anymore. So the cylinder heads are actually one component of those big engines. So we have a view over here, and you can see it's a quite complicated component because there's a cooling system inside of it. So you got hot water, you got actually water that gets hot, you get the explosion of the engine, and you also get some very, very cold places where actually there's water circulating in order to cool the engine. Of course, it was complicated for EDF because, well, we know how to do mechanics, we know how to deal with complicated problems, but we're not engine producers. It's not our main subject of work. And the main problem with these engines was that there was some bridge cracking through the valve. So if there's you can see the input of the air in the exhaust pipe, cracks appear in between. And of course, we thought that it was because of the cooling process. As you can see to the right image, there's a combustion chamber in which there's this explosion, and right above it, there's cold water circulating at about 20-25 degrees Celsius. So there is strong gradient of temperature between these two, and it's not very thick at all. So when the actually ASN, which is the authority that let EDF operates or not its nuclear power plants, they noticed that there were these cracks after Fukushima. They've been there for the last 30 years. We never had any issues with it, but because of what happened in Fukushima, they reopened these files, and they asked us to define the maintenance program that we had for these engines. And the main question was, can the bridge cracks, they propagate up to motor failure? And motor failure in this case will be a little bit part that would enter the engine and will block the piston. So it was a problem that we never faced before. I mean, these cracks were documented for years. It was open, there was no problem, but we had to prove something out. So here's a big summary of all the tasks that were done using Code-aster in order to answer this question of the French authorities. So it's separated into 6 parts, which is a classical, I would say, study in mechanics. The first part is around the materials. I will not focus too much on it because it's a Code-aster-day, of course. And then afterwards, I will go into more details with every part of the simulation. So the first part was about the material. It's a material that actually we were not used to because we have some specific types of steels usually in canals in our power plants, and now we had to work with a new cast iron that is not the type of materials we're usually using. So we did some few tests within EDF in order to get the properties. And what we saw is that when we were doing some cyclic compression tests, we had a dissymmetric behavior. So basically the stiffness of the material seemed to be different when you were working with it in tensile and compression. And that was actually explained afterwards because the material was actually not a very good one. It's not produced by EDF, right? We buy these engines, so we have to deal with the material once we have it. And what we saw is that as soon as you have some tensile stress in it, some micro cracks appear. And of course, you have less area afterwards in order to take back the stress. So we have a different stiffness that appears in compression and in tensile. So afterwards, for the modeling, we need to take into account such behavior. And at the end, we did some fatigue analysis. I don't know if some of you know about fatigue, but here we will model it using a Paris law, and the exponent is around between 6 and 7, which is probably the worst fatigue materials I've ever seen. So as I said, this engine is we buy it and we have to deal with it. So the idea was to try to take into account that. So in order to do that, we developed a specific constitutive equation, which is something that is not available through all finite element codes. So we have the mFront interface, which is a little software that is included within Code-aster-day, also open source, in which you can easily write constitutive equations. So basically, if you know the equations, you just have to write equations, and then Code-aster-day will be able to read it. It's a specific language oriented for differential equations, I would say. So we managed to reproduce the experiments we had using a new constitutive equation that was, well, some specific functionalities in order to take the symmetrical parts, so the compression and the tensile parts. So as you can see, the results were quite satisfying. Once we have that, we did the CAD model and the mesh. So as you can see, it's a very complicated component with holes everywhere, and the cooling system is also very complicated. And we didn't have any plans. We had, well, no, we had some 3 plans from 1968 with most of them no coats on it. So it was complicated to get actually the right size. We had to measure quite a few things, and also I will, if I dare to say, imagine a little bit what happens in between. And then from that we managed to do a sane mesh. So when I say a sane mesh, it's, at the end we will do a fatigue analysis, so there will be a crack inside of our mesh. Here we first started with a sane mesh, and we managed to have some very, very, very small elements around where there will be a crack, so we know we can capture what happens over there. As you can see, it's a very complicated mesh, around 600,000 nodes. So that's, if you look at it, it's in 3D, so we're close to 2 million degrees of freedom for that problem. Once we have a mesh, we decided to add cracks in it. So the cracks were added where we were actually seeing them experimentally. So what we did is we use another software called Z-Cracks, which can allow you to easily insert cracks in the same mesh. So this is an external software which we had the license. So we developed 3 meshes in order to have every crack possible that we saw. So you can see in the center here the mesh of the crack, and there's a zoom right afterwards. So we used a 20 millimeter crack because it's the biggest we've ever seen experimentally. So that was our reference, knowing that the whole space is 28 millimeters. So the crack is quite huge compared to what was available. Once we have the mesh, we decided to do some thermal simulation. So we didn't have much information about what happens in there. And of course, we could have done some simulation of the whole explosion, but that will be some complicated CFD simulations. And what we actually wanted to do was the effect of the thermics on the material and the loadings behind it. We were not really interested in modeling the whole explosion. So we modeled everything as a big exchange condition that was function of the radius. So as you can see to the bottom right, here's the temperature of a point when you start the engine. So you, in a few seconds, or I would say a few minutes, you reach between 300 and 400 degrees Celsius. So it's a bit hot in the center. And then afterwards, we ensure that the few measuring points we had while we computed using these exchange conditions were not too bad. So we get a profile which might not be the exact real ones, but it's sufficient in order to model the thermic part of the material. So for us, it was quite satisfying. And at the end, of course, there's a shutdown of the engine, so the water starts pumping a lot. and then it takes quite a lot of time to reach 0 degrees Celsius. So here's a little presentation, I would say animation of what happens. So first we start the engine, and then so we see the temperature is very, very, very huge over there because this is where the explosion is. We get the hot temperatures where we expect it to be, so between the bridges. So we're quite confident that our temperatures are maybe not perfect, but they actually model not so badly the reality, or at least what will happen in the material afterwards. So this simulation, yeah, afterwards there was a shutdown, is completely temperature-wise. So there's no mechanics yet, only temperature, in order to do mechanics afterwards. Which actually is my next point. So we did the mechanical simulation of a cycle of actually starting and closing up the engine. We had some boundary conditions here in order to ensure that there was no rigid body motion. Here we do not consider what happens mechanically, because we had information that led us believe that the main problem was the rise of temperature. What happens inside is not very important. At the end, the loadings are not very huge. What is important is the rise of the temperature and the temperature gradients. This is where most of the stresses come from. So in order to do that, well, we first did the simulation on the same mesh, and what was very interesting is that we saw that at the end, I would say, of the temperature rise, so when you start the engine, there is significant compression. I don't know if you can see over here. There is significant compression over here because of the gradients, and this has induced plasticity. And of course, afterwards, when the cooling part arises, well, there is a stress redistribution because of the process and because of the irreversible process of plasticity. At the end here, there is significant stress state that is tensile, not in compression, because we have, at the end you need to ensure that you respect the fact that you're in quasi-static state. So tensile stresses arise, and this is exactly where the cracks appear. So there's no crack yet, but we are already quite confident that our model is not so bad because it can reproduce a little bit of the stress state that happens locally. And if we look more carefully, at the end of the beginning, we see there is a very, very strong gradient of the stress state, that inside there is tension, but on the outside there is compression. And then it's the other way around afterwards. And what's very interesting is that we see that when there is tensile stress on the upper part, see if you look at the right part, there is compression inside. And as a consequence, if the cracks appear at the top of the component as is shown over here, it means that at one point the crack, if it propagates, will enter a compression part and it should be stopped. So at that moment, we were quite confident that our study wouldn't be too bad. If we can show that it stops, it means that it will never reach the other end, and therefore there won't be a whole crack in the structure which can induce a motor failure. So of course we had, afterwards we had to show it, but that's one of the main objectives was already met at that moment. So here's a little animation of what happens stress state-wise. On the right, it's, of course, it's not reality, it's times 70, I think. So we see that with the crack, it opens at the end because there is the tensile stress. Of course, there is stress concentration at the tip of the crack. So that's after one cycle. So our idea was that actually by testing our material, just by rising the temperature and then cooling off, we were creating cracks just by testing it. And this simulation actually proved it to us. So at the end, once we have this model, we had to compute afterwards the crack growth rate. So how quickly can is it going to propagate in order to ensure that it will not cause any motor failure. So we did some fracture mechanics analysis and also combined with the fatigue analysis. And we showed here, if you maybe most of you are not doing, I would say, fracture mechanics, but here we have what we call a stress intensity factor that describes how much a crack will propagate in fatigue. It's an indicator, and we computed for different cracks at different bridges, and we saw that we could compute this parameter. And using that, we can then use a Paris law in order to do fatigue analysis. And the fatigue was done using 1,500 start shutdown. So basically, that's the life of 50 years of the engine, unless something bad happens at the power plant, but that's the maintenance cycle that we have right now. And we saw that for the 3 cracks, we would have a margin of 7 millimeters, between 7 and 8 millimeters at the end. Basically, the more the crack propagates, the more it enters the compression area of the component, and it stops getting further. So we always add a margin of around 7 millimeters. So once you've said that, we showed that the cracks will stop, and as a consequence, it will not break any part of the engine, so the motor failure won't be an event. So as a summary, the question we had was this one: can bridge cracks propagate up to motor failure? In order to do that, we did some experiments to characterize the materials. We did some, we identified a behavior model using MFON in Code-aster in order to model this specific behavior. We managed to do a 3D complex shape of the CAD and the plans within Code-aster and Mecha, and all the thermomechanical study was done in Code-aster from the beginning of the temperature, the mechanical analysis, and the post-processing of the fatigue operators. And at the end, we managed to show that the bridge cracks cannot propagate up to motor brake for the cycle of this engine. So the idea here was to show you an example of how Code-aster can be used directly for EDF's problems, and a very industrial case, I would say, in which there are many parts. You saw there was some experiments in which we can afterwards use these experiments and capitalize what we've done. So as an example of what I was saying earlier, this new constitutive equation is now available for everyone within EDF in order to model this specific material. Of course, we do not usually work with these materials, so I don't know if it's going to be widespread, but now it's available for everyone. It's tested, and we can reuse it in the future. And if in 15 years, if there are some more questions about these specific components, we will still have it, and it's capitalized in the code. So this is one of, I would say, a good example of how Code-aster can be a good way to capitalize studies and models and knowledge in general. So thank you for your attention for this study.
Is there time for a few questions, or you are in how?
Yeah, sure.
Okay. I have a first question. A modeling approach I've seen in other occasions. Is it possible to model the same problem of crack opening, not employing a global model with the coarse mesh or reasonable mesh, but without actually the same mesh model, for example, without the crack, and isolate the displacement field at every time instant, at every temperature instant, for example, and then use that displacement field as a boundary condition for a local model, a global to local decoupled solution technique. Which is it possible? Is it?
It technically depends on your problem. In fracture mechanics specifically, it's a bit more complicated because the loadings are often a bit further. You got some significant non-linearities locally, and so your displacement field is dependent on the crack.
Okay.
So if you, it makes sense if you're far enough, but in our case it was not possible because we were so close to the explosion place that we had to cope with everything, and the boundary conditions were far. So we at first we thought of that, and then it's okay, it's not possible because with a small feasibility study, we showed that the fact that there was a crack changes a lot the displacement field where we actually needed it.
Thank you.
Yes?
First, compliments for the work. It's pretty amazing, and we did a lot of work with this. And I just wanted to ask you a couple of questions, clarification. The first would be the constitutive equation that you used. They seem to be related to the mechanical part of the material. So it's a fatigue process that you do the experiments.
Well, for the fatigue, also for the constitutive equations, both. The experiments were done for both, yeah.
But then you actually apply a thermal analysis. So what you probably would need is also to characterize your material in thermal form. plasticity in there. And so I wonder, what did you use these stress intensity factors for? Did you use them to actually predict the stress, the crack propagation? Were they used as a cracking criteria?
All right, so for the first question, for the thermal analysis, I did not focus on it, but we were lucky enough, well, the mechanical part was, I would say the effect of the thermics on the material behavior was characterized through constitutive equations at different temperatures. But also for the globally thermal analysis, we were lucky enough to have documentation from the producers of the engines that already had characterized them. So we took that, I would say, for granted up to a point, and we did a nonlinear thermal analysis in order to get our fields. So that's for the
constitutive equation as a thermal part.
yes, yeah, the thermal parameters were given by the producer. So I'm not allowed to show them because yeah, you can understand why. But yes, that was taken into account. And for the second part, actually the case, the stiffness, the stress intensity factors were computed using plasticity. They were not, it's not an elastic analysis. Of course, the fatigue part is a completely elastic analysis, but the factors here that were shown here were computed using an elastic approach, but the stress state was, and the displacement fields were given from a plastic analysis. So there is a consideration of our new constitutive equation over here. If we had done only an elastic analysis, it would be a bit higher because the stress state would be higher.
And then you use the stress intensity factor as a failure criteria.
Yeah, well, these SIFs were computed using a plastic behavior, and of course the Paris law is elastic because yeah, it doesn't work in the plastic conditions.
So the crack propagates according to the stress intensity factor.
Exactly. What I did get into details, but we added a significant amount of cracks, and we computed this stiffness, the stress sensitivity factors for different crack size, and we showed that the bigger the crack is, the smaller they are because they're getting closer to the compression state. Maybe I have an image afterwards. I don't know if I included it in this one. No, I didn't expect this question today. So, but yeah, so to answer more specifically, I don't know if I answered your question, but yeah, the plastic behavior is considered in computing the stress state. And then the post-processing part, of course, it's complicated to do some fatigue analysis with complicated equations considering plasticity. And actually, at EDF, we do it for some specific components, but not for this type of material. Yes?
To better understand how you simulated the cracks, I mean, did you detach the nodes locally, or the software that you used make these in a sort of automatic way based on the stress level?
Yes, so the crack propagation was performed explicitly, if I dare to say so. It was not, the length of the propagation was not computed by software. We could do it, but we didn't see the point in this case because we had to anyway analyze different crack sizes. In the way to produce the mesh, so actually the nodes are doubled and you add the discontinuity. So internally we did what we call the same mesh, so the mesh without the crack, and then we buy this software called ZCracks, which is interface inside of America, but you need a license in order to use it. And what it does is that you independently mesh the crack, so the surface of the crack, and then this software will make the junction of these two and produce a new mesh that will be different. It uses tetrahedral elements because it's easier to mesh, of course, but it can keep boundaries that already exist. So at the end, well, basically, if I go in more details, you specify the software where you want to have your crack. So it will extract a volume around that crack. You bring it to the software. The software will remesh that zone with the discontinuity inside of it, and then it brings it back to the original mesh, and you glue it back to the part in which you're using. And at the end, you get the exact same group of nodes, same group of elements, but you also have new ones around the crack. If you do some crack propagation analysis or just crack stability problems, you need to know where your front is, so you have all the groups already made for you.
Other question?
Any other question? Just a note, because, for example, I enjoyed the simulation because here in Modena we are pretty expert in engines. We basically do only that.
And we are not all.
And so I think that analysis is more than is better than what we usually do in our lab, because we do not test basically the propagation of the crack, just predict the crack. This is a pretty standard location, and I think that I have to note that this software is absolutely in line, actually pretty more developed than many other solvers we use or companies near here in Maranello use for the same purposes. So I think I have to say that the software is absolutely valid, and the results are extremely interesting.
Maybe if I can add a little something. Maybe I didn't focus on that at first, but within EDF, we knew that there was no problem with the component. It's because of what happened, the political events, and we had to do it. We had to, actually, the authorities asked us to go at such level, I would say, of precision, because for us it was clear that there was no problem. We've been using them for more than 35 years, and there was not a single problem, and we test them around 30 times a year. So there was no problem for us. The cracks have been there from the beginning, and with a very, very, I would say, handmade analysis, you can show that there is compression that appears somewhere, and then the crack will stop. But we were forced by the authorities to do it.
Yes,
so
if you say there is a crack for the average citizen, you say it's a
exactly.
crack, just throw away everything. But it's not so simple when there is an investment in beyond.
Exactly.
Okay.
Well, thank you for your comment.
If they are not
Okay, I think that we could go outside for the buffet, which is ready. Quindi facciamo una pausa per quanto riguarda la mattina. Abbiamo il buffet fuori e quindi possiamo servirci tutti sul banco all'esterno. Per quanto riguarda il pranzo, una cosa organizzativa, tutti i partecipanti che si sono registrati hanno il pranzo a buffet garantito, quindi insomma seguiteci dopo durante la pausa pranzo anche.
And if you have more questions, feel free to ask me. I'm here for the whole day. Thank you.